Okay, in this video, we are going to see the kinetic theory formulas. Before that, let's see the assumptions that are used to derive the kinetic theory equation. The first assumption is particles in a gas are composed of uh, internal energy. Internal energy is the sum of what? The sum of kinetic energy and potential energy. But in the case of an ideal gas, you ignore the potential energy. Therefore, the first assumption is the internal energy of the gas is entirely kinetic energy. That means there is no potential energy component, no potential energy, no potential energy. In other expression, no potential energy means there is no interaction between particles, no interaction between particles. There is no interaction between particles, no potential energy, or all the internal energy is entirely kinetic energy. This is in the case of an ideal gas. The second assumption is the collision between particles and with the wall is elastic. Collision is elastic collision. Elastic collision. This means there is no kinetic energy loss. No kinetic energy loss during the collision. Okay, the third one is, or the third assumption is, Newton's second law can be applied. Newton's second law can be applied. That means the motion of the particles in the gas is governed by Newton's second law of motion, and the fourth is the motion of the particles is random, not ordered. Random motion. Not ordered motion. Okay. The fifth assumption is a single particle is negligible compared to the volume of the gas as a whole. The volume of the gas as a whole. Okay, these are the assumptions that are made while deriving the kinetic theory equation. Next, let's see the derivation of the kinetic theory that relates the kinetic energy with temperature. Okay, derivation of the kinetic theory. Derivation of kinetic theory equation. Okay, let us consider a cube of length L. That is full of n number of particles. Okay, we have this y axis, we have this x axis, and there is a z axis. Okay, there are n particles in this container. N particles. N is the total number of the particles in the gas. Assume a single particle of mass m that moves in the x-axis with velocity vx. The length of this cube is L. The pressure exerted by this single particle. On this shaded wall is equal to force over area. The pressure is equal to force over area. But the force is by delta T. M times delta P by delta T. Delta P is equal to P final minus P initial. This implies the single pressure exerted by this single particle is equal to m times delta v by delta t over area. Let's see the speed. First, it's moving towards the x-axis. Therefore, it is vx minus vx in the I minus vx in the I. This is a change in speed or the change in velocity. We are only interested about the magnitude. Therefore, we don't worry about the direction. Therefore, this implies P is equal to m times minus 2 Vx over A delta t. But delta t is the distance between two collisions. That means L plus L over 2. That is 2L over 2. This implies P is equal to, let's ignore the negative sign, P is equal to m times 2Vx over A times delta t is let's cancel this one. Delta t is 2L over Vx. This is over time, and this is over not over time, over Vx, and this one is over Vx is equal to delta t. Okay, this is equal to m times Vx squared. Just when you multiply this by this one, it becomes squared over A times L. What is AL? AL is the volume of the cube. AL is the volume of the cube. This implies P is equal to m times Vx over m times Vx squared over volume m times Vx squared over volume. Okay, let's continue. This implies PV is equal to mVx squared. This is the pressure exerted by a single volume. Therefore, the total pressure P, this is the total pressure P, times the total volume is equal to m times Vx squared, Vx squared 1 plus Vx squared 2 plus Vx squared 3 plus Vx squared n. This implies the total pressure times the total volume is equal to n times m times Vx squared average. N times, this is the total number times the mass of a single particle times Vx squared average is equal to the total pressure times the total volume. Okay, let's continue. This implies PV is equal to n times m times V squared average over 3. This 3 comes from V squared average. Since the particle moves in space, it has x, y, and z components. Therefore, V squared is equal to Vx squared plus Vy squared plus Vz squared. But by probability, Vx is equal to Vy is equal to Vz. Therefore, Vx squared is equal to Vx squared is equal to or V squared is equal to 3 times Vx squared. Therefore, 1/3 of V squared is equal to Vx squared. This is how I substitute this 1 over 3. Okay, this implies PV 3 PV over N is equal to mv squared average. Just what I am interested is to make this mv squared a kinetic energy form. Therefore, I have to multiply both sides by half times 3 PV over N is equal to half mv squared average. mv squared average. This takes the form of average kinetic energy. This implies 3 over 2 PV over N is equal to, this is average kinetic energy. This is the average kinetic energy, but PV is equal to nRT. PV from the ideal gas equation, PV is equal to nRT. Therefore, let me substitute this from this. 3 over 2 N times RT over N is equal to kinetic energy average. Is equal to kinetic energy average. What is N? N is total number over Avogadro's number. This implies 3 over 2 N over NA times RT over N is equal to kinetic energy average. Okay, let's cancel N by N. Okay, let's continue. 3 over 2 R over NA times T is equal to kinetic energy average, but R over NA is equal to K. This is the Boltzmann's constant. R is constant, NA is constant. Therefore, this is another constant. Okay, 3 over 2 KT is equal to kinetic energy average. This is the equation that we need to derive. This equation relates average kinetic energy with temperature. Then our conclusion is kinetic energy is proportional to temperature. Kinetic energy is proportional to temperature. That is why we define temperature is a measure of average kinetic energy of particles in a substance. This is for monoatomic ideal gas. 3 over 2 kT for monoatomic ideal gas. For diatomic, there is another rotational, 2 rotational degrees of freedom. Then we have to add 2, then it becomes 5. This is X, Y, and Z degrees of freedom. But when the molecule becomes diatomic, we need to add 2 degrees, rotational degrees of freedom. Therefore, for diatomic, kinetic energy average is equal to 5 over 2 kT. 5 over kT. Therefore, this number indicates the number of degrees of freedom. If we are asked to calculate the total internal energy is equal to 3 over 2 N kT. This is equivalent to N times kinetic energy average. This is equivalent to N times half mv RMS squared. This is equal to 3 over 2 nRT. Or this indicates the total internal energy of the gas. Thank you.